Alright, so we have just finished talking about emission spectrums, but atoms can also produce two other kinds of spectrums called the absorption spectrum and the continuous spectrum. And so what I want to do is to illustrate to you how those other kinds of spectrums are going to be generated. And so I'm going to reproduce this chart over here. So first we need to have an object that is going to be glowing. And so in this particular case, it uses a light bulb. So this light bulb is going to be producing different colors of light. All right, now let's say that some of the light from this light bulb is going in this direction, and it's going to pass through a diffraction grating. So in the picture there, it's a prism, but let's go ahead and draw a diffraction grating so that the light from the light bulb is going to go through the diffraction grating, and it's going to be spread out into the rainbow of colors. So if you look at the picture over there, then you notice that you get all of the colors of the rainbow. So you get the complete Roy G. Biv thing. So all of these colors are going to be visible over here. Okay, but some of the colors are going to be brighter than other colors because it's going to be a black body spectrum. So that when you look at the black body spectrum of these colors, you notice that one of the colors, let's say yellow, is going to be brighter than, let's say, either red or violet over here and over here. So that's the reason why that curve underneath it goes up like that. It's illustrating that some of the colors are going to be brighter than other colors. That was a black body. All right, so let's now say that some of the light goes this way. Okay, it's going to go through a cloud of gas. I don't know what the cloud is made of, but it's made of some kind of gas. Now, certain frequencies of this light are going to interact with the atoms that make up this gas. And so it's going to cause, so in this gas, every atom has energy levels, and then when the light from this thing hits it, it's going to make those electrons jump, maybe from there to there or there to there, and then when they come down, they're going to emit light. So certain frequencies of light are going to be emitted by this cloud. Not all the frequencies of light, but only certain frequencies. Whatever frequencies are going to make the electrons jump. So this light is going to be scattered, and now let's say that I put my diffraction grating down here so that the light from here is going to go through the diffraction grating. It's going to spread out like that, okay, and then we're going to get now a emission spectrum. So down here you're going to get only certain colors of light, and the certain colors of light represent these transitions up here. So this one was the continuous, this one is the emission. Now what would happen if we put our diffraction grating over here? Now what's going to happen? So the light from the cloud is going to go through this, and if you put your eyeball over here, so you're looking in this direction, you're looking through the cloud at the light bulb. So what you're going to see is going to be all the colors that are being emitted by the light bulb minus the colors that were scattered, these colors here. So let me put it up here. So what you're going to see is it's going to be all the colors of the rainbow, and it's kind of hard to do, but but then it's going to have missing colors. And these missing colors correspond to these colors down here. So that this one here is going to be called an absorption spectrum because the colors of light have been absorbed by the cloud over here. So these are three kinds of spectrums that astronomers are interested in. They actually observe all three of them, and then you can tell different things about a star based on the kinds of spectrums that it emits. So what's the point? So you are an astronomer, and you have attached a diffraction grating to your telescope, and you've got all of this information about the spectrum of the star. What's it going to tell you about the star? So here's the information. Okay, the location of the lines, so what lines do you have, tells you what elements were inside the star. Okay, the brightness of the lines tells you the black body, and then that in turn we can use Wien's law, or Wien's law. So it's going to be called Wien's law. We could use that to determine the temperature of the star. Pretty impressive. Okay, we can look at the width of the lines. So some lines are like this, and some lines are like this. So some lines are thicker than others. So based on the width of the lines, we can determine, again, the temperature of the star by using the Doppler effect. Turbulence, we can also tell from the width of the lines. How fast is the star rotating? We can determine that from the width of the lines. We can determine whether the star has a magnetic field based on the width of the lines. And then we can determine, is the star moving towards us or away from us based on the shift of the lines. Okay, now it says here, properties in italics you will not need to know for the exam. Okay, so if you look at that, you'll notice that, for example, the turbulence and then the magnetic field are in italics, so you're not going to need to understand how this operates, but the other ones you do. And so what I've done is I put in the appendix an explanation for each of those. Okay, so Appendix 1 goes with elements present, location of the lines. So this shows you the lines that are associated with hydrogen and the lines that are associated with helium. And you see that they're at different places. So the position of the lines tells you what elements are inside the star. Okay, then this one you should understand. So you look for the brightest line in the spectrum, and then that's going to be the maximum wavelength, and then you plug it into Wien's law, and then you can calculate the temperature of the star. So that one I think you should understand. Okay, then this one here, okay, so let's go back here. The next one is temperature using the Doppler effect for the width of the lines. And so this is the explanation for it. If you don't understand the explanation, don't worry about it, but just understand that the width of the lines tells you the temperature of the star. Okay, this one is kind of out there, so I would not expect you to understand this explanation, but there it is, and that explains how it tells you about the turbulence. But you didn't need to know about the turbulence to begin with. Okay, this one you should be able to understand. So how fast is the star rotating? You can understand that because some of the light is coming towards you if it's on this side, and some of the light is moving away from you because it's on the other side, because the star is turning, meaning some of the light is coming towards you and some of it's Doppler shifted away from you. And so that's going to take the lines and spread them apart because it's being Doppler shifted to the right and also to the left. This one, don't worry about it, but this one shows how the magnetic field can be determined by using the Doppler effect, but it's not on the exam, so you don't need to know about that. And now this one is pretty easy. So this one is the Doppler effect. So we said that if something is moving towards you, it's going to be blue shifted. If something is moving away from you, it's going to be red shifted. So what does that mean? So let's say that this is the original spectrum, and now let's say that it is moving towards you. This star is moving towards the Earth. So that means it's going to be blue shifted. So that means that this line goes over here somewhere. And then this line goes over here somewhere. And then this line goes over here somewhere. So they're all shifted the same amount towards the blue end of the spectrum. Now the really bad thing about it is now the colors have changed. So let's say this one was red and it's shifted over here, so maybe it looks yellow now. And let's say that this one was green, now maybe it looks blue. So it can be very confusing looking at spectrums, trying to figure out what atom that they represent. Okay, so that completes this review, and we got one more. So come back, and now we're going to talk about telescopes.